All right, so this is Unit 4, Lesson 4. Unit 4 is talking about applications of differentiation. Lesson 4 is talking about related rates. And so we're kind of done looking at motion graphs, and now we're going to talk about related rates. And so in this lesson, we'll talk about related rates with rectangles and triangles. And so basically, given a context. So here we go. The length of a rectangle is decreasing. So it's decreasing by 1 inch per second, and the width is increasing by 3 inches per second. So here's a rectangle, the length 8 inches, but it's decreasing an inch every second. The width 11 inches, but it's increasing by 3 inches every second. What is the rate of change of the area? And so, okay, basically, how is the area of this shape growing or shrinking as time moves on? And so, rate of change is a derivative question. And so, basically, we're saying, okay, what is the derivative of the area? So, area of a rectangle is length times width. The derivative of the area with respect to time, we'd be taking the derivative of L times W in respect to t. And so this is an implicit differentiation, I guess you could say. The L and W are both variables, and they're being multiplied, so it's kind of like we're multiplying two functions, which means we have to use the product rule. The first function times the derivative of the second plus the second function times the derivative of the first, or L dw dt plus w dl dt. And so that's just product rule right there. And now we have all of these numbers, L dw with respect to time, w dl with respect to time. These are all numbers that are given to us in the original equation. So length is 8 inches, width is 11 inches. The dw, the change in width over time, is 3 inches per second. It's increasing, so it's going to be a positive 3. The length of the rectangle is decreasing by 1 inch per second, so it's negative 1. And we just got to keep in mind here, we're talking about our units for rate of change. We're talking about length divided by time. So, or sorry, area divided by time in this case. So area is going to be in inches squared, and time is in seconds. So all of our times we've given are in seconds. All of our length measurements have been in inches, so we're good to go on that. For the rest of us, now that we plugged in our numbers, though, we just kind of do some calculations and get our final answer is 13. So again, if we talk about the same question, but we talk about perimeter, what is the rate of change of the perimeter is a derivative question. So we're going to derive the formula for the perimeter of a rectangle. Rectangle is 2 times the length plus 2 times the width, and that gives us the perimeter. So the derivative of the perimeter with respect to time would be 2 dl dt plus 2 dw dt. Remember, we're doing implicit differentiation here, so we got the dl dt's and the dw dt's, all with respect to t going on, or all the variables with respect to t. And now we just plug in, we have dl dt, we have dw dt. That's our change in lengths over time for length and width. And then now, since we're talking about perimeter, our unit of measure is no longer squared, it's just inches, and it's still inches per second. Triangles. So same setup here. The procedure is analogous. We read the information from our question the same way. We just have a different formula for finding area. So the area for a triangle is half of the length times the height. For a right triangle, the height is the side leg, so that's nice and easy. We're deriving the area equation. So again, we have L times W. So again, we're going to do product rule, and we're going to derive L and W as variables implicitly with respect to t. So we have to use dw dt, dl dt. So here's our derivative equation. we have L dw dt, we have W and dl dt, so we plug those in, and then we get our final answer in terms of inches squared per second. And so this thing is a positive value, so that means this isn't growing by 6.5 or 13/2 inches squared per second. All right, what is the rate of change of the hypotenuse? Okay, so this is just my way of making the calculations that much more complicated. So you're welcome for that. Same setup though. How is this triangle? How's the hypotenuse growing? So we use our friend Pythagoras. Not really our friend, he's an old dead white guy, but we use his theorem nonetheless to find the area or the length of the hypotenuse would be the square root of the leg squared plus the width squared. Um, since we want to derive that, we'll write it as a rational exponent. So in this case, we have a chain rule. So 1/2 times the inside function to the power of 1/2 minus 1 is negative 1/2 times the derivative of the inside function. And so we have L and W as variables that we are implicitly deriving with respect to t. So we have 2L dl dt plus 2W dw dt. And let's see here. Yeah. If I rewrite this back as a radical, I'm going to put our negative rational exponent in the denominator as a square root symbol. The 1/2, the 2, and the 2, when I distribute or factor out the 2's, they cancel out with a 1/2. So we're left with this equation right here if we simplify algebraically. And then we just plug in our numbers for L's and W's and dLdT's and dWdT's. We're talking about a hypotenuse, so that's the change would be a length in time, so inches per second. It's a positive number, so we are growing. The hypotenuse is getting bigger over time. But all these examples are in a context. So, like if you think about it, the length of a triangle is decreasing by 1 inch per second, and the length is 8 inches. There's only so long this can decrease before the whole equation falls apart, and that's true for any of these examples. So we do have a domain restriction given to us by the context in these ones. But it doesn't really affect us on delta math, so I don't think we care too much, do we? What we do care about is that we can use this derivative concepts to model related rates of change in a context, which kind of helps round out our understanding of derivatives in general.